This will be conducted from 10 to 11:30 in the morning. Next session will be conducted from 11:45 to 1:15. That session will be on image reconstruction using deep learning, which will be taken by Dr. Manish Bhatt. And the last session will be conducted on implementation of image segmentation using deep learning. So in this way, we will complete day 5. This is a 6 days training program, short-term training program sponsored by AICT on image processing and its application. So we had so far 12 technical sessions in which we have learned about basics of digital image processing, image photography, image enhancement restoration, image and basic image processing operation using Python. Then we have also learned about natural language processing using recurrent neural network. Then we have started working upon neural network. So the one session was conducted on image classification using artificial neural network. Then one session was conducted on document image classification using computer vision. Then image captioning using recurrent neural network. Yesterday we had 3 sessions which were taken on convolutional neural network. So we learned about basic operation of CNN, then transfer learning for image classification, and then feature extraction intermediate layer of neural network. We have learned yesterday. So far we have completed image processing, recurrent neural network, natural language processing, and convolutional neural network. Today we are going to learn about the applications of what we have learned, like how can deep learning be used in medical applications, how can deep learning be used in image reconstruction and image segmentation. So last 2 days of this short-term training program is on application part of what we have learned, how to apply our learning for various applications of deep learning. So to conduct the session of on deep learning for medical applications, we have with us today Dr. Kuldeep Singh, Assistant Professor, MNIT Jaipur. Dr. Kuldeep Singh has received his PhD degree in computer vision from Delhi Technological University, New Delhi, India, and MTech degree in signal processing from Netaji Subhash Chandra Institute of Technology, New Delhi. He has worked as postdoctoral fellow at University of Alberta, Canada, where he was involved in development of deep learning based functional prototype for agriculture applications. Before joining MNIT, he has worked at Central Research Laboratory of Bharat Electronics Limited BEL Ghaziabad as scientist from January 2007 to March 2019. During this tenure at BEL, he has worked on various projects of National Bharat Electronics Limited in 2009 and 2011. He has been a reviewer of various IEEE transactions elsewhere and Springer Journal. I welcome Kuldeep sir in this technical session. And over to you, Kuldeep sir, now.
Good morning, all. Thank you, sir. Thanks for inviting. Thanks for the brief introduction. First of all, I have heard your schedule of previous days. I'm sure the participants have been benefited largely with the sessions. And since the basics of deep learning has already been covered, I think participants can better appreciate their application domain, specifically in the medical diagnosis area. So without wasting much time, I'll start my presentation now. All right. So in this 1.5 hour of talk, we will basically discuss various applications of deep learning, specifically in medical diagnosis. As far as agenda is concerned, we will briefly discuss what is deep learning, though you already have some sessions on convolutional neural networks. convolutional neural networks and deep learning, but still for the better understanding and readability of the participants, I'll briefly take an overview of deep learning and how it is different from traditional machine learning and artificial intelligence. We will discuss the footfalls of deep learning in the medical applications, some use cases of deep learning in medical diagnosis. Then we will see how models are being built using deep learning algorithms. What are different challenges when we are building the models? One of the major challenges is data size challenge. We will discuss the solutions of this data size challenge as well. We will talk about how do we test the models. Once the models are developed, how can we evaluate the performance of those models? We will talk about some of the popular data sets in the field of medical diagnosis, the MRI data sets, the X-ray data sets. So we will discuss about those publicly available data sets as well. In last, we will have a demonstration on how we can detect coronavirus using chest X-ray images. So that will be part of your practical exercise. So before diving into the application domain, I'll talk about these three terms, AI, ML, and DL. And I'm sure with the participating in this FDP or this short-term course, you must be able to differentiate between these three terms. These three terms are interchangeably used these days. And in our daily life, we frequently use these three terms. But there is a clear boundary between these. And let me discuss the boundary, let me define that boundary and how these terms are different. With the help of an example, we will differentiate between these three terms. So firstly, the term comes artificial intelligence. As you can see in the diagram here, artificial intelligence is at a higher level. It is at a higher hierarchy, and machine learning and deep learning comes as at the lower hierarchy, and they are also the sub part of the broader term, the broader aspect, artificial intelligence. The term artificial intelligence was coined somewhere in 1950s or 60s, where the idea was to mimic the human behavior, to enable the computers so that they are able to do the task which a human can easily do. So that's why artificial intelligence is also, we define it as any technique that enables computers to mimic human behavior. Traditionally, the part, I'm not saying that machine learning and deep learning is not part of intelligence, but I'm just talking about the portion which is not covered in machine learning and deep learning. I'm talking about the traditional AI part that was practiced somewhere in 1960s. What exactly was the idea of artificial intelligence at that time? At that time, the knowledge of human was being transferred to a computer or a machine, and with the help of some kind of rule engines, that is one type of AI that was being built at that particular time. And you must have also heard about, when we talk about rule engines, you must have talked about heard about fuzzy logic, where we somewhere quantify the reasoning. So in artificial intelligence, let's take an example how with the help of rule engine, a human knowledge can be transferred to computers or machine. Suppose you have to classify between different type of fruits. How can you classify that? With the help of artificial intelligence, there used to be some kind of if then else kind of rule engines. If the color of the fruit is red, the shape of the fruit is pear, and the weight of the fruit is 100 grams. So you can make a nested loop kind of rule engine, and if any example passes through these nested loops, if then else loop, then you can make a decision on this. If this, if not this, else this, and then finally you can infer the result from the based on how the information has been processed by the rule engine. Similarly, if you have to differentiate between orange and apple, so for apple, the rule engine will have a different conditions. If the color is orange and shape is square, then it will be classified as your orange. This is a basic layman example how rule engines and in traditional artificial intelligence we use to transfer the human knowledge on computers with the help of programming. We used to program, we used to transfer that knowledge in the terms of software programs on the computers. But this has inherent limitations. Always the knowledge cannot be quantified. As you have heard, studied fuzzy logic, there is no crisp boundaries. So there is fuzziness in decisions. These limitations of traditional artificial intelligence gave birth to machine learning. The term itself says machines will learn. Machines will learn from the examples. Some kind of examples will be provided to the machine, and they will learn from those examples. And whenever a new example or unseen or unknown example will be given to that machine learning, it will be able to identify that. I'm talking about the same fruit classification problem. We will provide images of different fruits along with their labels or their category. The machines will extract some kind of features out of it, and then it will be uh, trained. And once the model is trained, it will be able to classify any unknown or test image which was not part of the training. So that's why machine learning is more about ability to learn without explicitly being programmed. As in the case of artificial intelligence, where we used to program the computer, we used to transfer that knowledge to the computer in terms of programming. We have to hard coded programming for transferring the knowledge. But in the field of machine learning, there is no need of explicitly programming the computer. The machine should have an ability to learn. So that was the term machine learning. Now, going back to the example of that fruit classification, we will provide images with the labeled one. Labeled means this image belongs to apple category, this belongs to orange category, this belongs to banana category. And once this information has been given to the computer, it will extract some kind of features which are distinguishable in nature. Distinguishable means based on those features, it will be able to distinguish those images like color, shape, weight. But in the case of traditional artificial intelligence, we were providing that color to the program. But in the case of machine learning, they will extract that features automatically. So that is the brief idea about machine learning. Now comes deep learning. Deep learning is a specialized branch of machine learning which deals with neural networks, and it is advanced form of neural networks. In traditional machine learning, we have a limitation that we have to extract features, and those features are not generalized. We have to extract features based on the problem domain. Any feature extracted for face recognition might not work correctly for fingerprint recognition. Any features which has been extracted for crowd behavior analysis might not work for biometric recognition. So that was the limitation of machine learning. That was solved by deep learning. Deep learning is capable of extracting patterns itself automatically from the underlying data. Underlying data can be image, it can be audio, it can be text, any kind of data can be provided. It will be able to extract the features itself. So that's about deep learning. I hope I will be able to clarify between these three terms. Now, what exactly is deep learning? I'll not go much into details, as you have already discussed, have some sessions on deep learning and convolutional neural network, but it is more about extracting patterns, useful patterns, distinguishable patterns from the underlying data. How it is being done with the help of neural networks, and thanks to the new optimization algorithms, we are able to achieve higher performance. Neural networks, traditional neural networks used to be of one or two hidden layer, but in deep learning, the deep neural networks have large number of hidden layers so that they can extract meaningful or useful information from the input or underlying data. Now the next question comes, why now? Why deep learning has become popular in last 1 decade or so, less than 1 decade or so, though the deep learning basic building blocks of deep learning were available, like neural networks, perceptrons, they were available in 1950s. But why it has become popular now? The reason is, there are three reasons. Firstly, the big data, the availability of large volume of data for training these neural networks. These deep neural networks are data hungry neural networks. They need large volume of training data for training. So with the availability of large abundance of data, we are able to train these deep neural networks. One of the popular data set is ImageNet, which contains millions of images, and most of the modern convolutional neural network for image classification has been trained on ImageNet. Availability of hardware, you all must be aware that the specialized hardwares like graphical processing units, GPUs, they have made deep neural networks practically realizable. Then the availability of software like open source software, TensorFlow, Keras, Caffe, these softwares, you can train your models, build new models, and you can build practical applications using deep neural networks. So thanks to these three reasons, we are able to see the practical implementation of deep learning. As we can see, this is the basic difference between conventional machine learning pipeline and deep learning. I was saying that conventional machine learning used to have a separate feature extraction step, and this feature extraction step was not generalized. It was specific to particular problem domains. But in the case of deep learning, the feature extraction is, and the prediction is, the part of deep learning algorithm itself. It is, we have to provide the data, and the complete deep learning model involves extracting features and prediction in one step. Why deep learning? The hand engineered features we used to extract for in traditional machine learning are time consuming, brittle, and not scalable in practice. Why not? We can extract or learn underlying features directly from the data. As you can see here, suppose we are providing the facial images to the deep neural network. The initial layers, you must have studied, you must have learned about the convolutional neural network. In convolutional neural network, where the starting layers are responsible for extracting the low level features like lines and edges. As we go deeper into the convolutional neural network, mid level features are being constructed using these low level features like lines and edges. Mid level features like eyes, nose, and ears, they basically constitute high level features. By combining these mid level features, we can constitute high level features like facial structures in the later or final layers of the convolutional network there. Once we are able to compute these high level features, now we can easily apply any classification algorithm on these high level features, and it is easy to classify these features. That's the brief overview of convolutional neural network, which is a combination of convolution and pooling layer. Then we have fully connected layer. We have rectified linear unit, which is a activation layer, and it is non-linear in nature. It brings non-linearity into the network. So that's the basic idea of convolutional neural network. I think you have studied it in detail, so I won't go much into details of convolutional neural network. As you can see here, the starting layers computes the lines and edges, which is low level features. Then from these edges, shapes are being built by the middle layers, and these are mid level features. And finally, the last layers, the latter layers, will be able to constitute objects from the mid level features. And finally, they are being classified by the softmax layer. So now let's come to the point where we can discuss deep learning presence in the field of medical domain. Recently, in this current pandemic time, there's a scarcity of the RT-PCR based test kits, and this has basically helped researchers to find alternates of testing coronavirus. So the researchers have basically find an alternate method of detecting coronavirus from the COVID patients from the chest X-rays. So radiologists, they basically use deep learning algorithms to find signs of COVID-19 in chest X-ray images. So that is very helpful alternate solution in the times where we have scarcity or shortfall of testing kits. So this can provide an alternate solution for testing coronavirus. Then other usages like deep learning has helped in discovering new antibiotics. So discovery of antibiotic is a very complex problem, and our researchers end up in discovering same antibiotic again and again. But deep learning has shown promising results in the field of drug discovery and specifically in discovering antibiotics. Then a lot of companies like Google, Facebook, Microsoft, IBM, they are investing large uh, amount of money in the field of medical diagnosis. And thanks to deep learning, which have human comparable results, specifically in the field of medical diagnosis, they have surpassed human doctors as well. So a lot of companies are investing large volume of money in the field of medical diagnosis using AI or deep learning. So Google uses artificial intelligence to detect breast cancer by screening the mammograms. They are able to apply artificial intelligence or deep learning algorithm to detect the breast cancer. Then deep learning technique could improve cancer diagnostics. So based on using deep learning algorithms, uh, deep learning technique cloud, basically we can port our models on cloud. I'll show you in my demonstrations where a trained model can be put on Google Collab on the cloud, and we are just using that cloud services. So it can help you in cancer diagnosis. Then deep learning tools can easily identify common eye diseases. So uh, it has applications in multiple areas. We at MNIT, we are closely working with SMS Hospital and RUHS specifically for creating this chest X-ray data set for detecting coronavirus and building a comprehensive system where it can assist radiologists so that the radiologist can upload a chest X-ray images and it can diagnose and analyze the chest X-ray images and give results in timely fashion. Other use cases, like one of the major startup in US is Analytic, which has invented a device that combines the ability of a group of expert radiologists at detecting lung cancer nodules in CT images. And surprisingly, it is achieving 50% higher detection rate in testing conditions. Google's lymph node assistant, I think you must have heard about it. It is able to detect staged breast cancer from histopathology images with 99% success rate. And you will be surprised to know that where human doctors have scored as low as 38%. There's a software called AI Docs AI that is made for radiology image analysis, and it has been installed in more than 100 hospitals worldwide, and almost uh, radiologists were able to treat over 1 million patients with the help of this AI Doc software. Now, let's see more details how we can build models and algorithms. Let's take an example of COVID-19 detection. What we have to do is we should have a large volume of chest X-ray data set. We train a model or algorithm, and once the training is being has been completed, when we present a new test data or a chest X-ray image, it should be able to classify it into 3 classes, whether it is COVID-19, pneumonia, or normal class. Another example is diabetic retinopathy. It is a disease commonly found in diabetic patients. It involves damage to the blood vessels of retina, and sometimes it can lead to vision loss. That's why the diabetes patients are asked to regularly have their eye checkups. So in this type of system, basically what we have to provide the retinal fundus images to the model, and the model in turn should be able to distinguish between the test image whether it is normal or the retina is damaged. Another area where deep learning has been extensively utilized is MRI. The modality is the MRI. In the case of, specifically in the case of brain MRI, the segmentation of brain MRI is being done using deep learning algorithms, and based on segmenting different, the human brain contains different type of fluids, and the MRI image captures the structure of the brain, and with the help of MRI segmentation, we can segment these different type of volumes or liquid or fluid in our brain, and based on the size or volume of these matters or volumes in our brain, different type of diseases are diagnosed. So this deep learning based brain MRI segmentations helps us in diagnosing different type of diseases related to brain MRI. So automatic brain MRI segmentation is a crucial area where deep learning helps us. You can imagine like how many slices are being computed when we are taking a brain MRI. So that's the large volume of data, and it is being provided to deep learning. It can easily segment them, automatically segment the different slices of brain segment, a brain MRI. Another example is like breast cancer detection, where we use histopathology images. These are basically the microscopic images of blood smear, and the idea is to check whether the tissues are malignant or they are benign. Benign means they are normal. Malignant means they have symptoms of cancer. So we can, with the help of these histopathology images, we can train a model or algorithm, and this model and algorithm can help us in detecting cancer in histopathology images. Uh, this is more extensive list of healthcare applications of deep learning. One is like prediction of medical events like seizures and cardiac arrest. With the help of capturing EEG signals, uh, the epileptic seizure can be easily predicted or detected with based on the EEG signals. Also, deep learning based algorithms helps us in prediction of cardiac arrest. Drug discovery is another area I have already discussed about antibiotic discovery. Analysis of electronic health records, automatic medical report generation. That's also an interesting field where, based on the medical imaging modalities, like suppose we are giving a chest X-ray to a model and algorithm, it will automatically generate a report about the diagnosis report of that particular imaging modality, medical image modality. So that becomes very handy for the doctors, where the automatic analysis report has been generated from these modalities, from MRI images or EEG signals or radiology images. Then Alzheimer's disease detection, Parkinson disease detection, cyst segmentation, pharmacogenomics. This is study of how genomic variation affects a patient's response to a particular medication. And the list is endless. There are deep learning has been extensively used in the field of medical diagnosis, and there are large volume of applications in the field of medical. So let's have more specific applications. Suppose a radiologist has been given 3 samples of COVID-19 or multiple samples of COVID-19 and normal images, and when a new type of image is provided to the radiologist, based on the examples given to him or her, uh, you can easily detect whether this chest X-ray belongs to COVID category or the normal category. In the same fashion, it works. In the same fashion, uh, the deep learning algorithms also works. They are being trained on different examples, and based on the training, it will be able to, once the models are trained, whenever a new or unknown test image is provided to it, it has learned those features or extracted or automatic extraction of features from the training data, and now it will be able to classify the new image to a particular class. How do we build models? So with the help of the training examples, we provide thousands of chest X-ray images, and then the algorithms or models learn from those training examples. We provide images along with the labels. Labels means what category they belongs to. We can name these algorithms models as like deep learning, deep neural networks, they can be convolutional neural networks. So there can be different variants of these algorithms and models. So with the help of training data set and labels, we are able to train our models, build our models. So what is the process of it? So whenever we are training the algorithm and model, it will basically give us prediction probabilities. So in the starting phase of the training these models, they will give us the scores which are not close to the desired label. Suppose we have assigned desired label 1 for the COVID category and desired label 0 for the normal category. So in the starting, there will be large errors, uh, large errors since they are not trained. So once we start the training phase and multiple iterations has been done, the objective of this training or building the models is to minimize this error and make these prediction probabilities or scores as close as possible to the desired label. We formulate some kind of objective function where we have to minimize this loss or error, or we have to maximize or make it close to the desired label. So as the different iterations processes or different epochs are being executed while training, this loss becomes close to zero and the scores approaches to the desired labels. So that was the example of how models can be built using chest X-ray images. Now, with the help of histopathology images, how do we train our convolutional neural network or any model? Since the histopathology images are microscopic images, these are very high resolution images, and sometimes they might be of size of 1 GB or more. So in that case, it is not advisable to feed the complete high resolution image for the training or testing of these models. So what do we do is we sample different patches from these high resolution images, and these particular samples are labeled, and the models are being trained on these these patches being sampled from the histopathology images. Instead of feeding a complete histopathology image, we feed millions of patches which are being sampled from the larger image. And also at the time of testing, the large image is being divided into small patches, and these patches are being detected whether they belong to benign or malignant category. Popular convolutional neural architectures which are being which has been used in medical applications are Inception, V3, ResNet, DenseNet, SqueezeNet. We use UNet for MRI segmentation, 3D-Net. So there are large variations in architectures, and they are made specifically for medical applications. So the list is very large, but these are the popular ones which are being extensively used in medical applications. So how it works, you can see the diagram here. The input image is provided. Different type of filters are being applied on the input image by the convolution layer. Then some kind of activation function or rectified linear unit works on them. Then we have a pooling layer. Pooling means we are basically reducing the dimension of the input feature map. Then as the information being transferred in a hierarchical manner through this convolutional neural network, and then finally we have a fully connected layer where we flattens the complete nodes, and finally a softmax or some kind of classifier is being applied here to classify it to a particular category. So that's the basic pipeline of analysis of any MRI or medical modality using convolutional neural network. One of the major inherent challenge while building deep learning based model is the data site challenge. As you are aware, uh, it's very difficult to sample data sets for medical imaging. So, or also you will have scarcity of uh, images for minority class. Like specifically in the case of COVID-19, I was reading somewhere the first deep learning based model was trained on almost less than 100 COVID-19 chest X-ray images. So you can understand the scarcity of data available for training of these models. So that is basically the data site challenge, and there is a solution to it. And the solution, we call it transfer learning or fine tuning of pre-trained network. The idea is we can transfer the learning from one domain to our medical domain. The idea is we basically take a pre-trained connet which is being trained on some other images like natural images, or suppose a convolutional neural network which is being trained to classify between cats and dogs. It is trained on millions of images. We take it, we fine tune it for our domain with the help of limited images which we have in our data set, and then this fine trained connet is being used for our problem domain. Now, how it works, why it will work? It has been trained on some other domain. How it will work for our domain? So it is basically the starting layers of the convolutional neural networks involve extracting lines and edges. So whether those lines are edges are being extracted for dogs and in cats, or they are being extracted for chest X-ray images, the task is similar. So we need not to retrain those starting layers. Whether they are trained on different data set, their task is to extract lines and edges. And they can achieve that task on medical image domain as well. So that's why the starting layers of any pre-trained connets are freezed. Only the later layers which are responsible for extracting high level features like detailed features into the chest X-ray images, those layers are only retrained. And for training one or two or three last layers, this much of data available with us is sufficient for them. So that's why we use fine tuning for solving the data site challenge. Another way of solving this challenge is data augmentation. If we have a small volume of data available with us, what we can do is we can generate new images from the existing images. With the help of these techniques, like we can have a zoom function on it, we can rotate, we can change the contrast, we can flip, translate, input some kind of color noise, or combination of these different techniques of data augmentation. Now, once we are done with building the models, we will talk about how do we test these models, because testing is very important after building the model, so that we can know that how well they are performing, how well we have built the model, will they be able to give us good results. So basically, whenever we are creating a data set, this data set is being divided into three parts. One is training, another one is validation, and the last one is testing. Training data set is being used for building or development of the model. Validation is for tuning of parameters, and the testing is basically for performance evaluation of the developed model. Sometimes we use cross-validation methodology to have a better training framework. In cross-validation, basically, what we do is we divide these sets, training and validation, in small portions, and we recursively, iteratively use different set of these small portions of data sets for training the model and validation of the model. Suppose we have divided the training set into 5 small portions and validation into 5 small portions. So we randomly pick these small portions for training and validations, and this is being done iteratively, where all the all the images of training as well as validation are being part of training as well as validation. What are different challenges? One major challenge is patient data overlap. Suppose the same data from the same patient is part of training as well as testing. That could be a challenge. Then annotation of ground truth, like labeling of the data, labeling of medical data, which is a big challenge specifically for in the medical domain. So patient overlap, what kind of problem can happen in case of patient overlap? Suppose a patient has taken chest X-ray in different time slots, one in suppose in January, one in July, and the X-ray taken in January is being part of training dataset, and the chest X-ray taken in July is part of testing dataset. So in that case, it will be over optimistic performance by the model. Why? It will memorize some kind of information from the chest X-ray, which is patient specific, not disease specific. As in the case here, the patient is wearing a necklace here. In both the chest X-rays, it is wearing the the necklace. Suppose while training, we have labeled this chest X-ray as normal image. So while training, the model will memorize this necklace as a feature of normal patients. Now, whenever we provide a chest X-ray of this particular patient with this particular chest X-ray wearing a necklace, it will categorize it into a normal patient because it has memorized that necklace. So that is the problem. We call it patient data overlap. And what's the solution to it? Solution is there should be no overlap of patients in different data sets. Ensure to have data from same patient in one set, either in test or in validation or in training. Also assign patient IDs to the modalities or the images. Usually we assign in different domains like in image classification or object detection. We just assign image IDs. We are not concerned with what kind of image it is. But specifically in the medical domain, we have to assign patient IDs. A unique patient ID should be assigned to a particular image. And we should ensure that images for a particular patient ID should be part of one of the data set, either it is training, either it is validation or testing. And now how do we sample these data set? How do we construct these data set? So sample test data set, then validation set, and then training. This sequence must be followed whenever we are sampling these data. Firstly, we will sample the test data set, then we will go for validation one, and then finally we will go for the training. And there is a condition to it. Whenever we are sampling a test data set, we should have at least X% minority class. Ideally, it should be 50%. So suppose if we are building or we are curating a data set for COVID chest X-rays, we should have 50% of chest X-rays belonging to coronavirus and 50% to normal category. Then validation set should also have same distribution of the classes that of the test data set. If test data set have 50% of minority classes, the validation data set should also have 50% of minority classes. And remaining classes we can make as a part of training data set. So that's the methodology of sampling of sets. Next problem associated when we create data set and test these data sets is ground truth annotation, labeling of data sets. Now, specifically talking about histopathology images, there is a large difference of opinions among the pathologists or doctors when they analyze these histopathology images. So there can be a difference of opinion, and some pathologists may say that this histopathology image belongs to normal category, or this some of them might say that it belongs to malignant. So what's the solution to it? Solution is consensus voting. We can show the samples to multiple pathologists or doctors and then have a consensus voting. We can assign the class which the majority of the pathologist assigns to this particular histopathology. Suppose 2 out of 3 are saying this belongs to malignant class, we can assign malignant label to this particular histopathology. So we can have consensus voting of different pathologists. Also, there is a very not cheap, very costly solution to this down-tooth labeling. In, in, uh, while assigning the labels to histopathology images, we can check another modalities for that particular disease, whether that patient have that disease or not. We can diagnose it with another modalities. So if another modalities tells us that yes, this person have cancer, then we can assign that particular label to that of the to that particular histopathology. But that's very costly solution. Next comes, once we have built the model, we have tested the model. Now let's evaluate the model. Let's see the performance of that model, how it is performing on the test data or unknown data subjected to it. So let's take an example. Suppose we have 10 test images. On the left hand side, this 10 this is the ground truth label of those 10 test histopathology images, whether they belong to malignant or benign category. Now we have two models, and we provide these 10 test images to these models, and the models are giving us these results. Model 1 has given assigned malignant category, sorry, uh, benign category to all the 10 test images. Positive means it's a diseased case, and negative means it's a normal case. So malignant if it's a disease. So if model is giving you positive, that means it is correct. So you can see here both the models have 50% accuracy. So in my opinion, the model 2 is better than model 1, since model 2 is able to somehow distinguish between these two categories. But model 1 is not able to distinguish between them. It is assigning the negative category to all the 10 ground truth images. So that means the accuracy, which is basically probability of correct detection, is not the right measure to evaluate the model. So we have multiple evaluation metrics to see the performance of these trained models. And what are these? Firstly, the confusion matrix. You can see a table here. On the left hand side, we have ground truth, and here we have model output. So if in the ground truth, an image is labeled as positive, positive means the diseased case, and the model has also predicted it as positive, we call that subject as true positive. Similarly, if a image is labeled as negative in ground truth and model has also predicted it as negative, we call it true negative. In this table, these two parameters are of interest for us. The value of these should be highest, and the other two ones, the false negative and false positive, the value should be as close to 0. Based on these four parameters, true positive, false negative, false positive, and true negative, we define certain parameters like sensitivity, recall, that talks about correctly detected items or correctly detected modalities. So it is basically the ratio of correctly detected items to all items that should be detected. That means in ground truth, whatever images are labeled as positive out of those images, which all images has been predicted as positive by the model. So that is basically related to sensitivity. Similarly, specificity is related to the negative ones. Out of the images labeled as negative, which ones are being predicted as negative by the model? It's a ratio of true negative by the total images labeled as negative. Then we have ROC curve, receiver operating curve, which is basically a graph between sensitivity and specificity. So with this example, let's calculate how we can calculate sensitivity and specificity. Given the ground truth of 10 images, the model is giving us this output. Out of these 10 images, what will be the value of true positive? So out of these 10, 5 are basically the positive ones in ground truth. And out of those 5 positives, the model is able to detect 4 as positive. So that's why we define the true positive number, true positive is 4. And out of 5, 1 has been categorized as false negative. Similarly, in the case of negative or benign, 2 are false positives and 3 are true negatives. So sensitivity is basically the ratio of true positive, the first row of this confusion matrix. So true positive divided by true positive plus false negative. So that is 0.8. And then specificity, that is basically true negative divided by the second row of the confusion matrix, true negative plus false positive, that is 0.6. Now this basically tells you the correct picture of the performance of the model. Ideally, their value should be 1. Why 1? Because the true positive, ideal case is true positive should have a value of 5 and the true negative should have a value of 5. The rest of the 2 parameters, false negative and false positive, should be 0. That's why sensitivity will become 5 divided by 5 plus 0 as 1 and specificity will become 5 divided by 5 plus 0 as 1. That is considered as the best performing model. Another one is ROC curve. So whenever we build a model, so once the model is being built and a new test image is provided to this model, it gives us a score or prediction probability, and this score is subjected to the threshold, and if it is greater than the threshold, it will be classified as positive, otherwise it will be classified as negative. So with the variation of this threshold, your value of sensitivity and specificity will change. So we can draw a graph between true positive rate and false negative rate and for different threshold values. Ideally, the area under this ROC curve should be close to 1. We call it AUC, area under curve. And so whichever curve out of it is having highest AUC will be considered as the best curve or best model. So that's how we can evaluate a performance of the model using ROC curve. Now we'll talk about publicly available data sets. Publicly available data sets for different medical modalities. We have Open Neuro, we have UK Biobank, TCIA, Abide, ADNI. These are basically MRI data sets. So these are publicly available. You can train your models on these data sets and test your model. Then we have chest X-ray data set, Chexpert, chest X-ray 14. These have different number of different type of patients and for training or testing your models. Then we have histopathology related data sets like BRACHIS, which is being extensively used for cancer detection. And then MIDOS, we have ChemiaPath 24. So these are the different data sets for medical modalities. So let's summarize what exactly we have discussed as of now. We talked about the basics of deep learning. We differentiated between different terms of AI, ML, and DL. We talked about convolutional layers, different layers of convolutional neural network. We talked about how do we build the model. Uh, we also have taken data size, challenge, and different solutions to it, like transfer learning, where we can take a pre-trained convolutional neural network, which is trained on some different domain, and we can transfer it to our medical domain. Uh, Data size challenge, where we have a smaller number of images for our medical modalities. We can also use data augmentation, where we can create new images by changing the contrast or rotation or flipping the same image, and we increase the number of images for training. Then we discussed about testing of models. Uh, we should ensure that there should be no overlap of patients in different data sets. There was also a challenge of ground truth annotation or labeling of the images that is being solved using consensus voting. We discussed different evaluation metrics for the models like sensitivity, specificity, ROC. We also see that accuracy is not the correct measure while evaluating the performance of these type of models. So that was the summary of what we discussed. Now we will see a demonstration of detecting coronavirus using chest X-ray images. So I'll show you the demonstration on Google Collab. Google Collab is a cloud-based service where you can execute, you can train your models, you can test your models, you can build a code and port it on Google Collab and run it, execute it there. So I think you can see the Python script here on Google Colab. This is a Python script which is being
Hello, sir.
developed by our team. Can you see that?
Hello, sir. It is
Yes, sir. It is visible. You can zoom it, sir.
Zoom, please.
Let me zoom it then. Just a minute. Can you see it now?
Yeah. Now it's okay.
All right. So what we have done is we have trained a convolutional neural network using chest X-ray images, in which there are three classes. One is COVID-19, one is pneumonia, and one is normal category. So we have curated different chest X-ray images from publicly available data sets for COVID-19 chest X-rays, and trained our own convolutional neural network. And once it is trained, I'm not able to show you the training part because it consumes a lot of time. It took us around 1 day of training that model. So once that is trained, I have saved it in my Google Drive. And now with this inference Python script, I will use that particular trained model. I'll give a chest X-ray image as an input, and we'll see how it can give us the result in terms of those three classes, which category the particular chest X-ray belongs to. So we'll start with let's define the TensorFlow version. Since TensorFlow version 2.x is also available, but I have used TensorFlow version 1.13. So we firstly define that we force it to use TensorFlow version 1.13. So we are executing it. Currently, it is connecting to the cloud. So this script is saved on my account and my drive. Once it is being connected here, it provides us. You can see here we have access to 12 GB of RAM and hundreds GB of disk, and in the background we have access to different GPUs. So once this TensorFlow version is selected, I'll mount my drive. Why do we need to mount the drive? Our Google Drive can be mounted here and the data can be saved. Data can be saved to our drive, and that data can be accessed here. So I am putting the authorization code here, and it will connect it. The reason why we have to import our Google Drive to Google Collab is, since the storage provided by the Google Collab uh, stay with us for 24 hours only. After 24 hours, whatever data we have uploaded to Google Colab will be deleted automatically. So that's why, to avoid the loss of the data, we store our data on Google Drive. And then now it says that mounted at content at G Drive. Now here you can see that it is being mounted as G Drive. So my drive is mounted here. In my drive, I have a folder COVID-19. In COVID-19, I have a model which was being already trained earlier, and I have saved it here. It is saved in the form of .pb. So whenever I'm accessing this model, I have to define that path in my script. So along with this COVID model, I have some test images. So these are the test images in JPEG format or PNG format. I'll take these images while testing. I'll define the path of these images in my script to infer the results. Also, I have some data sets which I used during my training of this model. So once the drive is mounted, I'll import some libraries like NumPy, TensorFlow, then Computer Vision, OpenCV. Now there comes the importing of the let me close it. So we have three categories: normal, pneumonia, and COVID-19. It's a mapping to the numerical number to a particular class. Normal belongs to 0, pneumonia belongs to 1, and COVID-19 belongs to 2. Then we initialize the TensorFlow session, and as I told you, we'll define the path of the trained model. So the path is, I showed you that it's in the content Z drive, my drive, in the folder COVID-19 and COVID-19 model. And we should, the model is model 8485. And then we use the image tensor and the prediction tensor. So let's import it first. So it says that it is restoring, the TensorFlow is restoring the parameters from this. I have used TensorFlow for training and testing the model. So once it is, the parameters are restored, now what I will do is, I will read an image in that particular folder, the test image folders. You can see the path, content, G drive, my drive, COVID-19, test images, and that's the name of the file. Once it is read, I'll show it how it looks. I'll do some pre-processing on it, change, resize of it, and then I'll use that prediction tensor which I defined earlier when I have imported that trained model, and it will give me the prediction. Now the prediction will tell me the mapping, whether it is 0, then it will be normal, or so let's execute it. I think it got disconnected somewhere. It is initializing again. So maybe due to the network connectivity, it disconnected. Now I'll run it again. You can see here it has read an chest X-ray image. I have shown that image as I am show, and That's the prediction. It has predicted it as belonging to pneumonia class. And as you can see here, it has assigned the scores to a particular class. And if the score is greater than a particular threshold, it will be classified to that particular class. In this case, it has highest score to pneumonia class. That's why it is being classified to pneumonia class. Now, what I will do is I'll take another image for testing. In my drive COVID-19 folder, I have test images, and from the test images, suppose this, let's take this image. So we copy this path and paste it here. Now instead of the earlier image, we are using this image now. So let's run it again. Now it will detect COVID in this particular chest image. This is the different chest X-ray image from the earlier one. And the prediction is COVID-19. You can see that the score is highest here for COVID-19 class, that is 0.995. So that is basically, suppose let's take another example of normal one, comment this one, and let's run it. Now you can see this chest X-ray belongs to normal category since the confidence or the prediction score is highest for the normal class, that is 6.641. That's why it is being classified to normal category. So that's a small demonstration where we can detect coronavirus using chest X-ray images. You can build your own model. There are some GitHub repositories available where you can download your data sets. You can use existing convolutional neural networks like Inception V3, ResNet, and fine-tune it for your training, your data set of coronavirus chest X-rays, and then use it for testing purpose. So that's all for the demonstration part. Now you can have your question answers if any queries you have.
Sir, participants are asking to share the link of the code which you have shown.
I'm really sorry, the code won't be able to share because we are currently working on it on a project somewhere. So I won't be able to share the particular code. But yes, on the web, on some GitHub repositories, you can find similar codes where you can have inference on chest X-ray images. So you can have that.
Okay.
Participant have asked what new research we can do in CNN. See, CNN, currently people are applying CNN in different domains, specifically in medical, agriculture, computer vision problems. So you can find, one of the ways you can find new applications where you can apply convolutional neural network, or you can develop a new architecture of CNN which is efficient in terms of training or performance. Another way is nowadays, not specifically to CNN, but all these architectures we have discussed are supervised machine learning. What you can focus is on unsupervised deep learning. That is a current topic, or researchers working in that direction. So you can explore unsupervised deep learning. Please share the code and PPT. I'll share the PPT definitely. Code, I'll see if I can share somehow. Since with the code we have model also, which is almost, the size is almost 1 GB. So model can't be shared, and if the model can't be shared, the code is of no use for you. Thank you, participants. Thanks for your attention. Thanks for your time. Thanks for patiently listening me. Thank you. Thanks a lot.
So thank you very much, Kuldeep Singh, for taking this technical session on medical image classification. and it was indeed a very good session for all those who are working in this area. So I extend my sincere thanks to you, sir. Thank you very much, sir.
Thank you, sir. Thanks for the invitation. Thank you.
So now in this way we are closing session 1 of day 5, which was on medical imaging, and now we will move forward to the next session. The next session is at 11:45, and that session is a very good session for all those who are working in image processing, and image reconstruction is the new area in image processing where image will be reconstructed using deep learning. So in-depth knowledge will be given, code will also be shown to you, some experiments tutorial will also be given to you. So you all can join back at 11:45 for medical for image reconstruction using deep learning, which will be taken by Dr. Manish Bhatt. So thank you for participation in session 1. We have been monitoring attendance also of each session, and we are keeping track of all these things. We have already shared all study material which I have received from resource person with you, and other things will also be shared with you. Please be connected and join back at 11:45 for session 2 of day 5. Thank you very much.